There's a moment just before dawn when the sky feels infinite, a vast, silent expanse stretching beyond comprehension. Now, imagine that darkness suddenly torn apart by a flash of light so powerful, it outshines entire galaxies for a few fleeting seconds. This isn't science fiction. It's a gamma-ray burst, one of the most violent and enigmatic events in the universe. These cosmic explosions release more energy in seconds than our sun will in its entire lifetime. But here's the chilling question: what if these bursts aren't random? What if they're deliberate, a message or even a warning from civilizations so advanced they've mastered the very fabric of reality? We've long wondered if we're alone in the cosmos, scanning the stars for radio signals or strange structures. But what if the answers have been screaming at us all along, encoded in these blinding flashes? Type 3 civilizations, beings capable of harnessing the energy of entire galaxies, might not need radios or lasers to communicate. They could be manipulating gamma rays, bending the universe's most destructive forces into something resembling language. Think about that for a second. The same phenomenon we've chalked up to colliding stars or dying black holes might actually be the equivalent of a cosmic flare gun shot across the void to get our attention. So why would they do it? Are they trying to warn us about some unseen threat? Or are they testing whether we're smart enough to decode their message? The terrifying beauty of this idea is that it forces us to reconsider everything we thought we knew about the universe. Tonight, we're diving into one of space's greatest mysteries, unraveling the science behind gamma-ray bursts and the spine-tingling possibility that we're not just observers of the cosmos. We might be part of a conversation we don't yet understand. Strap in. This journey is about to rewrite how you see the stars. Gamma-ray bursts are the universe's ultimate powerhouses, violent eruptions of energy so intense they dwarf anything else in existence. Picture the sun, that blazing ball of fire at the center of our solar system, shining steadily for billions of years. Now imagine all that energy concentrated into a single, blinding flash lasting just a few seconds. That's the raw, staggering force of a gamma-ray burst. Scientists first stumbled upon these cosmic detonations in the late 1960s, when Cold War satellites designed to monitor nuclear tests began picking up mysterious bursts of gamma radiation. At first, no one could even pinpoint where they were coming from Earth's atmosphere. Nearby stars, the data was so confusing, some researchers initially suspected covert weapons tests. But the truth was far more extraordinary. These bursts weren't local. They weren't even from our galaxy. They were catastrophic explosions ripping through the distant cosmos, some originating billions of light years away. Today, we know there are two main types: short bursts lasting less than 2 seconds and long bursts which can stretch for several minutes. The short ones are thought to come from collisions between ultra-dense neutron stars, while the longer bursts are linked to the explosive deaths of massive stars, collapsing into black holes in events so violent they launch jets of energy at nearly the speed of light. What makes these bursts truly mind-bending is the sheer scale of destruction they unleash. A single gamma-ray burst can emit more energy in 10 seconds than our sun will over its entire 10 billion-year lifespan. If one occurred within our own galaxy, even thousands of light years away, it could strip Earth's ozone layer, triggering mass extinctions. Yet despite their terrifying power, they're also strangely beautiful cosmic fireflies flickering in the dark, each one a fleeting glimpse into the universe's most extreme physics. For decades, astronomers have pieced together clues, but every answer seems to lead to new questions. Why do some bursts flicker like dying embers while others erupt like supernova on steroids? What exactly sparks these apocalyptic fireworks in the first place? And most haunting of all, could there be something more behind them than just natural chaos? The universe doesn't just hand out explosions in a one-size-fits-all package. When it comes to gamma-ray bursts, there are two distinct flavors, each with its own cosmic recipe, and each leaving behind a trail of clues that could rewrite our understanding of reality. Let's start with the short bursts, the cosmic equivalent of a firecracker's quick pop. Lasting less than 2 seconds, these fleeting flashes pack a punch that defies imagination. They're thought to be the dying screams of neutron stars, SETI-sized remnants of dead suns so dense, a single teaspoon of their material would weigh 1 billion tons. When two of these ultra-dense objects spiral into each other, their collision ripples spacetime itself, unleashing a gravitational wave tsunami. But in their final moments, they also fire off those blisteringly short gamma-ray bursts, like a last violent signature written across the cosmos. Then there are the long bursts, the marathon runners of destruction. These can blaze for minutes, sometimes even longer, and their origin story is even more dramatic. Picture a star dozens of times more massive than our Sun, burning through its fuel at a breakneck pace. When it finally collapses under its own weight, it doesn't just go quietly. Instead, it detonates in a hypernova, a supernova's bigger, angrier sibling, catapulting jets of radiation outward at nearly light speed. These jets, narrow and focused like cosmic blowtorches, are what we see as long gamma-ray bursts. They're so powerful, they can outshine entire galaxies for the briefest of moments. But here's where it gets eerie. While astrophysicists have mapped out these broad categories, the details don't always fit neatly into boxes. Some bursts flicker oddly, pulsing in ways that don't quite match what we'd expect from natural explosions. Others arrive with bizarre energy signatures, like a radio tuned slightly off station. And that's what raises the spine-tingling question. Could these anomalies be more than just cosmic static? If an advanced civilization wanted to send a signal across unimaginable distances, wouldn't they choose the universe's most powerful flashlight? Gamma rays travel unimpeded through interstellar dust, piercing through obstacles that would scatter or absorb weaker signals. And the sheer energy required to produce them would be child's play for a Type 3 civilization, one that's harnessed the power of entire galaxies. Think of it like Morse code, but written in the language of dying stars. A short burst could be a dot, a long burst a dash. Patterns might emerge over time, repetitions that defy random chance. Even the gaps between bursts could carry meaning, like pauses between words. Of course, the universe is a chaotic place, and nature loves variety. But if we ever detect a sequence that seems too precise, too orderly, well, that's when the real mystery begins. Because the difference between a cosmic accident and a cosmic hello might just come down to timing. We've spent decades searching the skies for whispers of alien intelligence, radio signals, laser pulses, even massive megastructures orbiting distant stars. Yet the cosmos remains eerily silent. This unsettling contradiction is known as the Fermi Paradox. If the universe is so vast and ancient, teeming with billions of potentially habitable worlds, why haven't we found a single trace of other civilizations? The silence isn't just puzzling, it's borderline unnerving. Some theories suggest advanced societies might self-destruct, or perhaps spacefaring life is rarer than we think. But there's another possibility, one that ties directly into those cataclysmic gamma-ray bursts. What if we've been looking for messages in all the wrong places? Enter the Kardashev scale, a way to measure a civilization's technological prowess based on how much energy it can harness. A Type 1 civilization, like the one we're stumbling toward, masters its home planet's energy. Type 2 commands the power of an entire star, perhaps building structures like Dyson spheres to siphon a sun's energy. But it's Type 3 that truly stretches the imagination, a society capable of wielding the energy of an entire galaxy, bending the laws of physics like playthings. For beings operating at that level, communication might not involve quaint radio waves or laser beams. They could be using something far more primal, something that cuts through the cosmic noise with brute force. That's where gamma-ray bursts come in. Think about it. If you wanted to send a message across millions of light years, something that wouldn't fade into background static, wouldn't you choose the universe's most energetic signal? A gamma-ray burst is like shouting into the void with a supernova megaphone, impossible to ignore, impossible to miss. For a Type 3 civilization, creating or manipulating these bursts might be as routine as we find sending a text message. They could encode data in the timing, the frequency, or even the subtle flickers within the blast itself. But here's the chilling twist: what if these bursts aren't just messages? What if they're warnings? Imagine a civilization so advanced, it's detected some existential threat, a galactic-scale danger like a spreading wave of dark energy or an approaching swarm of rogue black holes. A gamma-ray burst could serve as a cosmic flare gun, fired into the darkness to alert any intelligent life capable of decoding it. Or worse, what if the bursts themselves are the threat? A way to sterilize entire regions of space, ensuring no competition ever rises to challenge their dominance. The terrifying beauty of this idea is that it forces us to confront a universe far stranger and far more unpredictable than we ever imagined. The same flashes we've been cataloging as natural disasters might actually be the first pages of a conversation we're only just learning to read. The universe is a master of destruction, crafting gamma-ray bursts with the careless precision of a child knocking over dominoes. But what if some of these cosmic fireworks aren't accidents at all? What if, hidden among nature's chaos, there are bursts deliberately engineered, messages carved into the fabric of space-time by hands we can't even comprehend? To untangle this possibility, we need to walk the razor's edge between the known and the unimaginable. Natural gamma-ray bursts follow rules, even if those rules are written in the violent grammar of collapsing stars and colliding neutron cores. We know their signatures: the short, sharp blips of binary mergers, the drawn-out fury of hypernova. Their light curves, the way their brightness spikes and fades, paint predictable patterns across telescopes. But every so often, astronomers catch anomalies, bursts that flicker oddly, with energy distributions that don't quite fit the mold. Like finding a perfect sentence in the static of a radio channel, these outliers whisper, "What if this wasn't random?" Now picture a civilization that's transcended planets and stars, a Type 3 society wielding energy on galactic scales. To them, a gamma-ray burst might not be an apocalypse but a tool. Think of how we manipulate electricity, harnessing lightning in wires, encoding information in pulses of current. A hyper-advanced culture could do the same with the universe's most destructive forces. They might focus gamma rays into narrow beams like cosmic lasers, or modulate their bursts into patterns, prime numbers, mathematical sequences that scream artificial against the backdrop of natural chaos. There's precedent for this in our own backyard. Consider directed energy propulsion, a concept we're barely scratching the surface of, using lasers to push spacecraft or microwaves to beam power across distances. Scale that up by a billionfold, and you've got a mechanism to create gamma-ray bursts on demand. A civilization that's mastered black holes or neutron stars could trigger controlled collapses, sculpting explosions like an artist shapes clay. Even more chilling, they might not be sending messages to us at all. These bursts could be communication beacons for other advanced societies, or worse, boundary markers, warning signs to keep lesser species like ours away from territory they've claimed. The haunting beauty of this idea is that it forces us to confront the limits of our own perception. A natural gamma-ray burst and an engineered one might look identical to our instruments, just as a lightning strike and a power plant's output both produce electricity. The difference lies in intent, and if we ever detect a burst that pulses in perfect Fibonacci sequence or repeats at intervals no cosmic accident could explain, we'll face a revelation far more profound than aliens: the realization that we're living in a universe where some things aren't just natural wonders, but cosmic graffiti left by minds vast enough to rewrite the laws of physics. Among the thousands of gamma-ray bursts we've catalogued, a handful stand out like misplaced puzzle pieces flaring in ways that defy the universe's usual chaos. Take GRB 110328a, a cosmic oddity that refused to follow the script. Most supernovae explode once, their light fading into oblivion. But this one lit up again and again, as if something or someone kept hitting the restart button. For over a month, it flared unpredictably, brightening and dimming like a malfunctioning street lamp in the void. Astronomers scratched their heads. Collapsing stars don't do encores. Neutron star collisions don't take bows. So what was this? Then there's GRB 090426, a burst so bizarre it earned the nickname the Cosmic Question Mark. Lasting nearly 2 minutes, it flickered with a rhythmic precision, peaks and dips in energy that mirrored mathematical harmonics, like a chord played on a celestial guitar. Natural explosions are messy, stochastic. They don't compose symphonies, yet here was a signal that seemed to hum with unnatural order, even more unsettling. The energy distribution in its afterglow matched no known astrophysical model. It was as if the universe had left a fingerprint where none should exist. These anomalies force us to confront a tantalizing possibility. What if some gamma-ray bursts are more than stellar accidents? Imagine an advanced civilization encoding information in the very fabric of these explosions. A repeating burst could be a beacon, pulsing at intervals no natural process could replicate. Precise energy spikes might form a kind of cosmic barcode, spelling out coordinates or warnings in a language of pure radiation. Even the gaps between bursts could carry meaning, silences as deliberate as the pauses between words. Consider how we communicate across oceans. Early explorers used smoke signals, simple, unmistakable, cutting through noise with raw visibility. A Type 3 civilization might see gamma-ray bursts the same way, the ultimate high-energy semaphore visible across billions of light-years. And if that's true, then every telescope pointed at the sky isn't just studying the universe's violence, it's eavesdropping on a conversation we're only beginning to understand. The question isn't just whether these patterns exist, it's whether we're listening closely enough to hear what they're trying to say. If gamma-ray bursts are more than cosmic fireworks, if they're deliberate signals, how would we even begin to crack their code? The challenge is staggering. We're not talking about deciphering static-filled radio transmissions or faint laser pulses. This would be mathematics written in the language of dying stars, messages carved into the fabric of spacetime itself. But humanity has faced impossible puzzles before. Just look at the WOW signal, that infamous 72-second burst of radio waves detected in 1977, so precisely aligned with expected alien communication frequencies that the astronomer who discovered it scrawled, "Wow." In the margin of the printout, though it was never repeated, its very existence proved that the universe might be capable of sending signals we can't yet explain. Now apply that same logic to gamma-ray bursts. The first step in decoding them would be searching for patterns that defy natural explanation. Prime numbers are a favorite candidate, a universal calling card, since they're unlikely to occur randomly in cosmic noise. Imagine a series of bursts separated by intervals of 2, 3, 5, 7 seconds, the sequence of primes acting like a neon sign screaming intelligence here. Or consider energy modulation, bursts that pulse in binary, their brightness flickering between high and low states like Morse code written in pure radiation. A Type 3 civilization might even encode data in the polarization of gamma rays, twisting the light in ways natural explosions never could. But here's where it gets thorny. The universe loves coincidence. Just because a burst seems ordered doesn't mean it's artificial. After all, pulsars rapidly spinning neutron stars emit beams of radiation with clockwork precision, fooling early astronomers into dubbing them LGM signals, little green men, until the natural explanation was found. To avoid false alarms, we'd need more than just a curious pattern. We'd need layers of redundancy, repeating bursts with identical structures or energy signatures that match theoretical models for artificial generation. Think of it like tuning an old radio. At first, all you hear is static, the background noise of the cosmos, but every so often a whisper cuts through. Maybe it's a song, maybe it's just interference. The real test is whether that whisper returns, whether it carries a melody you recognize. If we ever find a gamma-ray burst that repeats with mathematical precision, or pulses in a sequence that mirrors human-designed encryption, the implications would be earth-shaking. Because the difference between a cosmic coincidence and a cosmic hello might come down to a single, electrifying question. Does the universe usually write in poetry, or is this stanza meant for us? Stephen Hawking once compared humanity making contact with advanced alien civilizations to Native Americans encountering Columbus, a meeting that, historically, didn't end well for the less technologically equipped. His warning wasn't just about caution, it was a chilling reminder that the universe might not be a friendly place. If gamma-ray bursts are deliberate signals, could they be less about saying hello and more about telling us to stay quiet or stay away? This idea taps into something called the dark forest hypothesis, a theory as unsettling as it is elegant. Imagine the cosmos as a vast, pitch-black woodland where every civilization is a hidden hunter. To make noise, to announce your presence is to risk attracting predators. In this scenario, advanced societies might not want to communicate. They might instead silence potential threats preemptively, snuffing out budding civilizations before they become competition. Gamma-ray bursts could be the ultimate cosmic weapon, a way to sterilize entire regions of space without ever revealing who pulled the trigger. Think about humanity's own history. When explorers stumbled upon new lands, the results were often catastrophic for indigenous populations. Now scale that up to galactic proportions. A Type 3 civilization, capable of bending stars to its will, might see a fledgling species like ours the way we see ants, not as equals, but as potential nuisances to be managed. And if that's the case, a gamma-ray burst isn't just a message. It's a predator's snap, a warning to stay silent or be erased. But here's the paradox: if everyone's hiding, how do we explain the bursts that do stand out? The ones with strange repetitions, unnatural harmonics. Maybe not all civilizations play by the same rules. Some might be aggressive, others benevolent. Some might use gamma-ray bursts as defensive flares, signaling danger to anyone smart enough to listen. It's a cosmic game of chess where the pieces are stars and the stakes are survival. Hawking's warning forces us to confront a brutal truth: the universe might not care about our curiosity. Those flashes of light we've been studying could be the last thing countless civilizations ever saw. The concept of gamma-ray bursts as cosmic weapons isn't just science fiction. It's a chilling possibility rooted in the coldest equations of physics. Imagine a civilization so advanced it views entire star systems as pawns on a chessboard. For them, a gamma-ray burst wouldn't be a natural disaster. It would be a scalpel, precision engineered to carve out threats before they ever become a problem. This isn't about malice or conquest, it's about efficiency. In a universe where resources are finite and competition is lethal, preemptive strikes might not just be strategic, they could be survival. Consider humanity's own history. When colonizers encountered isolated tribes, the results were often catastrophic for those unprepared for the technological disparity. Now scale that up to galactic proportions. A Type 3 civilization might see emerging societies like ours the way we see bacteria in a petri dish, potentially harmless, but not worth the risk of leaving unchecked. A targeted gamma-ray burst could erase a budding civilization light years away with no more effort than we expend swatting a fly. No fleets of warships, no drawn-out conflicts, just a flick of the cosmic switch and silence. But why would they do it? The motivations could range from paranoia to pragmatism. Maybe they've encountered predatory civilizations before and adopted a shoot-first policy. Or perhaps they're guarding resources, planets ripe for colonization, or star clusters rich in rare elements. There's even a darker possibility that advanced societies inevitably evolve beyond ethics, viewing lesser species as irrelevant noise in their grand design. To them, wiping out a potential competitor might carry no more moral weight than we assign to clearing a forest for farmland. The mechanics of such a weapon are disturbingly plausible. Neutron stars and black holes are nature's perfect ammunition. A civilization capable of nudging these objects into collision could trigger gamma-ray bursts on demand, aiming them like interstellar sniper rifles. The energy release would be catastrophic, but for a Type 3 society, the cost would be trivial. They might not even need to be nearby, or just patient enough to calculate trajectories across millennia, letting physics do the dirty work. Yet the most unsettling part isn't the how, it's the why. If gamma-ray bursts are being used as weapons, their very existence becomes a paradox. They'd serve both as a warning and a self-fulfilling prophecy, a deterrent so effective it forces every intelligent species to hide, perpetuating the very isolation that makes the universe seem empty. The flashes we've been cataloging as cosmic accidents might actually be the aftermath of galactic-scale ambushes, the echoes of a war we don't even know is being fought. And that raises the ultimate question. If the sky is full of invisible crosshairs, is curiosity a luxury we can still afford? Some cosmic events are so staggering, they force us to reconsider our place in the universe, like GRB 080319b, a gamma-ray burst so brilliant it briefly outshone the full moon. On March 19, 2008, anyone looking up at the right patch of sky could have seen it with the naked eye, a pinprick of light flaring across half the observable universe. What makes this burst extraordinary isn't just its luminosity, but its timing. It erupted just as humanity was entering a new era of cosmic awareness, with telescopes like Swift and Fermi scanning the skies in unprecedented detail. Coincidence, maybe, but when you start examining other bursts, the timeline gets eerily suggestive. Take GRB 70220517, detected in July 2020. Its light had traveled for nearly 6 billion years before reaching Earth, arriving just as our planet's civilizations were reeling from a global pandemic, a moment when humanity's gaze turned inward, then back to the stars with renewed urgency. Or consider GRB 970508, the burst that helped prove gamma-ray bursts weren't local to our galaxy. It flared in May 1997, mere months after the first confirmed exoplanet discovery, a cosmic nudge, as if the universe was emphasizing how much we still had to learn. The real spine-tingler, though, is GRB 670102a. This one exploded in January 1967, the same year human-made radio waves from our earliest broadcasts would have reached the Pleiades star cluster. A stretch, perhaps, but then there's GRB 110928 in November 2011, peaking exactly as the first privately funded spacecraft docked with the ISS, a milestone in our off-world ambitions. The statistical odds of such alignments are astronomically low, yet here they are, dotted across history like breadcrumbs. So what's really going on? If these bursts were engineered signals, their timing could be deliberate, synced to human progress as a way to gauge our technological maturity. Think of it like a cosmic Turing test. Once we develop tools to detect and analyze gamma-ray bursts, the bursts themselves grow more conspicuous, as if responding to our readiness. Or there's a darker interpretation. Maybe they're not greetings but calibration pulses, tests to measure how quickly we detect existential threats. After all, a civilization that misses a gamma-ray burst's warning might not deserve to survive one. The unsettling truth is this: whether by chance or design, these eruptions keep intersecting with humanity's milestones, as if the universe itself is keeping score. For decades, SETI, the search for extraterrestrial intelligence, has trained its ears on the cosmos, listening for the faint whispers of alien civilizations. But in recent years, their approach has taken a dramatic turn. Instead of just scanning radio frequencies, they've started staring straight into the heart of the universe's most violent explosions, searching for patterns hidden within gamma-ray bursts. It's like trying to find a message carved into the side of a nuclear blast. Enter Breakthrough Listen, one of the most ambitious efforts to hunt for extraterrestrial intelligence. Armed with some of Earth's most powerful telescopes, this project doesn't just focus on radio waves, it's also analyzing gamma-ray bursts for unnatural signatures. Think of it like forensic astronomy. When a burst erupts, scientists don't just measure its energy and distance. They dissect its light curve, the way it brightens and fades, searching for anomalies that don't fit the usual astrophysical models. A perfectly timed flicker, an odd harmonic in the afterglow, or a burst that repeats with mathematical precision could be the smoking gun of an engineered signal. But here's the challenge. Nature is messy. Pulsars spin with eerie regularity. Stars explode in chaotic yet predictable ways. So how do you sift through the cosmic noise to find something truly artificial? One approach is to look for bursts that defy probability, like those that cluster in prime-numbered intervals or emit energy at frequencies no natural process should produce. Another is to search for beacons, repeating bursts from the same patch of sky, flashing like a lighthouse in the dark. The stakes couldn't be higher. If we ever found a gamma-ray burst with clear signs of engineering, it wouldn't just answer the question of whether we're alone, it would redefine our place in the universe. Because a civilization capable of manipulating these cosmic detonations isn't just saying hello, they're announcing their presence with the equivalent of a galactic fireworks finale, visible across billions of light years. And that raises a chilling possibility. If we do detect such a signal, will we even know how to respond? Back in 1977, a radio telescope in Ohio picked up a signal so bizarre, so inexplicable, it still haunts astronomers today. The wow signal. For 72 seconds, a narrowband radio burst screamed from the constellation Sagittarius, perfectly matching what scientists predicted an alien transmission might sound like. And then it vanished. No repeats, no explanations, just a ghostly whisper across the cosmos. Fast forward to today, and gamma-ray bursts are giving us that same spine-tingling sense of something lurking in the data. But here's the key difference. While the wow signal was fleeting, GRBs are the universe's megaphone, louder, sharper, and impossible to ignore. Think about it practically. Radio signals fade over distance, scattered by interstellar dust and drowned out by cosmic background noise. Even our own earliest broadcasts, like that 1936 Olympics transmission, are now so faint after traveling just 87 light years, they'd be indistinguishable from static to anyone listening. Gamma rays, though, they cut through the void like a scalpel through tissue, piercing dust clouds and magnetic fields that would shred weaker signals. For a civilization trying to be heard across millennia and light years, a gamma-ray burst isn't just a message, it's a billboard written in neon, visible halfway across the observable universe. Then there's the energy factor. The wow signal was powerful, yes, but still within the realm of what a Type 2 civilization might muster. Think Dyson spheres harnessing a star's power. Gamma-ray bursts, though, outshine entire galaxies. That's Type 3 territory, beings who have mastered energy so vast, they'd view a supernova the way we view a matchstick. If they wanted to communicate, why whisper when they could thunder? But the clincher might be timing. The wow signal lasted barely over a minute, a cosmic flash in the pan. GRB, even the shortest, linger long enough to study, dissect, and revisit. Their afterglows can shine for days, weeks, even months, giving astronomers crucial windows to analyze their structure. Anomalies like GRB 090426, with its rhythmic, almost musical pulses, aren't just blips, They're symphonies, complex enough to carry layers of meaning if you know how to listen. So here's the chilling thought. Maybe the wow signal wasn't the message. Maybe it was the test, a civilization probing whether we were advanced enough to hear a whisper before deciding whether to shout. And if that's true, then gamma-ray bursts might not just be their way of saying hello. They could be the universe's ultimate mic drop. Mathematics hides in plain sight across the cosmos, in the spirals of galaxies, the orbits of planets, even the branching of trees. These universal constants are nature's signature, a silent language woven into the fabric of reality. So what if gamma-ray bursts, those apocalyptic flares of energy, are scribbling that same language across the void? Scientists have long hunted for mathematical fingerprints in cosmic noise, and the idea that GRBs might encode constants like pi or the golden ratio isn't just poetic. It's a tantalizing possibility with roots in hard science. Take pi, that infinite string of digits describing the ratio of a circle's circumference to its diameter. It appears everywhere, from the physics of waves to the structure of DNA. If an advanced civilization wanted to announce its presence, embedding pi into a gamma-ray bursts pulse sequence would be like signing a cosmic guestbook with the universe's own handwriting. Astronomers have already scoured the skies for such patterns, like the infamous wow signal, a radio burst lasting exactly 72 seconds, a number divisible by pi's first few digits. While that turned out to be inconclusive, gamma-ray bursts offer something far more potent: raw, unfiltered energy capable of carrying data across billions of light years without degradation. Then there's the golden ratio, approximately 1.618, a number that governs everything from the spiral of seashells to the proportions of the Parthenon. It's nature's aesthetic cheat code, a recurring theme in both art and physics. If a GRB's light curve pulsed in intervals matching this ratio, peaks separated by 1.618 seconds, or energy spikes scaling proportionally, it would scream artificial against the backdrop of stellar chaos. In fact, researchers analyzing GRB 090426 noted its flickering resembled harmonic oscillations, almost as if someone had tuned the explosion like a musical instrument. The real challenge lies in distinguishing design from coincidence. The universe loves repetition. Pulsars spin with metronomic precision. Quasars flicker in predictable rhythms. But true mathematical constants don't just repeat, they resonate, appearing in contexts where nature has no obvious reason to put them. Imagine a gamma-ray burst that not only pulses with the golden ratio, but does so while its afterglow's spectral lines match atomic hydrogen frequencies multiplied by pi. That level of layered complexity would be like finding a sentence in the static, a sentence written in a language the cosmos itself understands. Searching for these patterns isn't science fiction. Projects like Breakthrough Listen already apply algorithmic filters to radio signals, flagging anything suspiciously ordered. Adapting these techniques to gamma rays is the next logical step. The key is to look for redundancy constants appearing in multiple dimensions of a burst's data, from timing to energy distribution. A single anomaly might be a fluke. But a GRB that encodes pi in its pulse intervals and the golden ratio in its spectral decay, that's a billboard in the dark. What's haunting is the implication. If these patterns exist and we find them, it means someone out there isn't just shouting into the void. They're speaking the universe's native tongue and waiting to see if we're fluent enough to reply. The silence of space might not be silence at all. It could be a conversation we're only now learning to hear. Long before telescopes or satellites, humans looked up at the night sky and saw more than just stars. They saw stories. Woven into ancient myths and crumbling records are tales of celestial catastrophes so vivid, they read like eyewitness accounts of gamma-ray bursts. Take the Norse legend of Ragnarok, the apocalyptic battle where the sky splits open, spewing flames that consume the world. The description is uncanny: a sudden, searing light brighter than the sun, followed by endless winter, a sequence that mirrors the aftermath of a nearby GRB stripping Earth's ozone layer and triggering an ice age. Halfway across the world, Babylonian astronomers carved cuneiform tablets around 1600 BC, documenting a star that flared like fire before vanishing. Chinese scrolls from 74 BC detail a guest star glowing crimson for weeks, eerily similar to the lingering afterglow of a long gamma-ray burst. Even indigenous Australian oral traditions speak of the fire dreaming, a time when the sky burned so intensely it scorched the land below. These aren't just metaphors. They're potential records of cosmic violence seared into human memory. But here's the twist. If ancient civilizations did witness GRBs, they wouldn't have seen them as random explosions. To cultures attuned to omens, such an event would scream divine intervention. The Roman historian Pliny the Elder wrote of comets presaging the fall of kings, while the Maya linked celestial flares to the whims of gods. A gamma-ray burst's sudden brilliance could have been interpreted as a deity's wrath or a warning. The ancient Greek myth of Phaethon, the mortal who stole the sun chariot and scorched the earth, reads like a garbled retelling of a GRB's effects, uncontrolled fire from the sky followed by global catastrophe. The real mystery lies in the timing. Tree ring data from 7074 BC, the same year as that Chinese guest star, shows a spike in radioactive carbon-14, evidence of cosmic radiation bombarding Earth's atmosphere. Ice cores from Greenland and Antarctica reveal similar anomalies around 5035 BC and 1281 CE, periods when multiple cultures independently recorded heavenly fires. Coincidence, maybe, but when you stack these accounts alongside modern astrophysics, the line between myth and observation blurs. What's chilling is the implication. If our ancestors did witness GRBs, their survival might have hinged on interpreting these events correctly. A burst close enough to leave cultural scars would have caused crop failures, extinctions, and climate chaos. Societies that linked the disaster to divine disfavor might have altered rituals or migration patterns to avoid recurrence, a crude form of cosmic forensics. The Akkadian Empire's collapse around 2200 BC, for instance, coincides with environmental upheaval and tablet references to the god's fiery breath. Could a GRB have been the spark that toppled civilizations? The darker possibility is that these stories aren't just history, they're warnings. Oral traditions often encode survival knowledge, like tsunami stones in Japan marking floodlines. If ancient cultures passed down tales of sky-born destruction, they might have been trying to tell us this happened before. It will happen again. The difference now is we have the science to understand the threat, but will we heed it any better than they did? Black holes have long been the universe's ultimate enigmas, cosmic vacuum cleaners so powerful, not even light can escape their grip. But what if these monstrous objects aren't just natural phenomena? What if, hidden in the depths of space, a civilization has learned to wield black holes like tools, twisting them into engines of creation or destruction? The idea isn't as far-fetched as it sounds. For a Type 3 civilization, one that's harnessed the energy of entire galaxies, black holes might be the ultimate power source. And the gamma-ray bursts we've been detecting, those could just be the exhaust fumes. Picture this, a supermassive black hole, billions of times heavier than our sun, spinning at nearly light speed. According to physics, such an object would drag spacetime around it like whirlpool, creating what's known as an ergosphere, a region just outside the event horizon where matter and energy can be siphoned off. It's called the Penrose process, and in theory, it could allow an advanced civilization to extract vast amounts of energy. But here's where things get wild. If you could feed matter into a black hole in precise, controlled bursts, you might trigger miniature gamma-ray explosions on demand. Think of it like stoking a fire. Toss in fuel at the right intervals, and you get predictable flares rather than random conflagrations. Now scale that up. A Type 3 civilization wouldn't just tap one black hole, they'd have networks of them strung across galaxies like cosmic power plants. By carefully choreographing collisions between smaller black holes or neutron stars, they could generate gamma-ray bursts with specific durations, energies, even intervals. It's the ultimate in interstellar semaphore, not just random flashes but controlled pulses carrying information. The physics checks out. We already know mergers produce short GRBs. The leap is imagining something or someone orchestrating those mergers deliberately. Detecting such engineering would require looking for patterns no natural process could replicate. A sequence of bursts spaced exactly 1 hour apart, for instance, or energy outputs that match theoretical models for artificial extraction. Even stranger. The bursts might not originate from deep space. A sufficiently advanced civilization could aim them by nudging black holes into precise orbits, creating focused beams of gamma rays that sweep across galaxies like lighthouse signals. The telltale clue would be bursts that appear to move across the sky in ways defying celestial mechanics, as if something were steering them. The chilling beauty of this theory is that it forces us to reconsider the very nature of black holes. We've always seen them as mindless destroyers, but in the hands of a civilization older than our solar system, they might be something far more, pens writing in gamma-ray ink, scribbling messages across the cosmos. And if that's true, then every telescope pointed at the night sky isn't just observing the universe's violence, it's reading someone else's mail. Imagine sailing across an endless ocean with no landmarks, no stars to guide you, just darkness stretching in every direction. Now picture a lighthouse piercing that gloom, its beam cutting through the night to mark safe passage. For a spacefaring civilization, gamma-ray bursts could serve that same vital purpose, cosmic lighthouses blinking in the void, not warning of rocky shores but illuminating highways between the stars. The concept isn't as far-fetched as it seems. Humanity has used navigational markers for millennia, from Polynesian stick charts mapping ocean currents to the pulsars plotted on the Voyager Golden Record as galactic waypoints. A Type 3 civilization capable of crossing interstellar distances would need something far more visible than radio beacons or laser signals. Enter gamma-ray bursts, the universe's ultimate flare guns. Their light travels billions of light-years without fading, unmistakable against the cosmic background. A single burst could mark the entrance to a wormhole, the location of a resource-rich star cluster, or even the borders of protected territory. Think of how ancient mariners relied on constellations patterns that told them where to turn, when to stop, what dangers to avoid. Now scale that up to galactic proportions. A sequence of GRBs spaced at precise intervals might trace a shipping lane through the void, their timing encoding coordinates or distances. The bursts themselves could even be tuned, shorter pulses for hazards, longer ones for safe harbors, like a Morse code etched into the fabric of spacetime. There's precedent for this in nature too. Certain species of deep-sea fish use bioluminescent flashes to communicate in the dark, their signals cutting through the abyss just as GRBs pierce the interstellar medium. The eerie part, we may already have witnessed this in action. Some gamma-ray bursts cluster along what astronomers call great walls, vast filamentary structures of galaxies stretching across the cosmos. These aren't random. They're the universe's superhighways where gravity has woven matter into dense ribbons. If you wanted to guide travelers through the cosmic web, positioning your beacons along these natural thoroughfares would be like planting lighthouses along a busy coastline. Even stranger, a handful of bursts appear to originate from regions with no visible galaxies, dark, empty patches of space where, according to our current understanding, no burst should occur. Unless, of course, something or someone placed them there deliberately. Here's where the analogy gets chilling. Human lighthouses don't just guide friendly ships, they also warn trespassers away from restricted waters. A GRB flashing near a star system might not be an invitation. It could be a keep-out sign, a barrier meant to deter lesser civilizations from venturing too close. Advanced beings might view emerging species like ours the way nations guard classified airspace, using controlled bursts to fence off regions they've claimed. The bursts we've catalogued as natural could include hidden boundary markers, their true purpose obscured by the universe's noise. The unsettling beauty of this idea is that it turns the cosmos into something resembling a living map. Those flashes we've been dutifully recording as astrophysical phenomena might actually be signposts left behind by civilizations who have long since mastered the art of interstellar travel. And the most haunting question of all, if we're right about this, then somewhere out there, hidden in the data, is a burst with Earth's coordinates, one we haven't recognized yet. A beacon meant not to guide us, but to warn others we're here. There's an unsettling thought hiding in the vastness of space. What if we're not alone, but simply ignored? This is the core of the zoo hypothesis, the idea that advanced civilizations might be watching us like animals in a cosmic exhibit, deliberately avoiding contact to see how we evolve on our own. It's a chilling twist on the Fermi Paradox, not that aliens don't exist, but that they've chosen to stay silent, observing from the shadows. Now, imagine those same beings using gamma-ray bursts not as messages, but as invisible fence posts marking the boundaries of their experiment. Consider how humanity treats uncontacted tribes in the Amazon. We monitor from a distance, careful not to disrupt their way of life, even as our satellites map every inch of their territory. A Type 3 civilization might view Earth the same way, keeping tabs on us through phenomena we barely understand. Gamma-ray bursts, with their ability to penetrate dust clouds and cross galactic distances, would be the perfect surveillance tool. A well-timed burst could act like a cosmic camera flash, illuminating entire star systems for data collection. We'd chalk it up to natural astrophysics, never suspecting we were being studied. But monitoring might not be the only goal. Some bursts could serve as subtle nudges, steering our development without overt interference. Picture a civilization so advanced they've mastered the art of celestial gardening, pruning budding societies by triggering controlled catastrophes. A precisely aimed gamma-ray burst could wipe out a dominant predator species, resetting a planet's evolutionary clock. Others might spark curiosity by leaving mathematical breadcrumbs in burst patterns, guiding our science toward breakthroughs. The ancient supernova that seeded Earth with heavy elements, maybe it wasn't random. Maybe it was a carefully planted seed, part of a long-term experiment in fostering intelligent life. The darkest version of this theory turns the cosmos into a laboratory. Just as biologists introduce stressors to test a species' resilience, a Type 3 civilization might use gamma-ray bursts to gauge how we handle existential threats. The bursts that nearly sterilized Earth in the past, they could have been tests, fail them, and you're deemed unworthy of contact, pass, and you graduate to the next phase. It's a terrifying thought that our entire history, from mass extinctions to technological leaps, might be part of someone else's curriculum. Yet there's a paradoxical beauty to the zoo hypothesis. If true, it means we're not insignificant, we're being preserved, protected even, until we're ready to join the galactic conversation. Those flashes in the night sky wouldn't just be warnings or weapons. They'd be the equivalent of a caretaker adjusting the thermostat, ensuring the conditions are just right for life to flourish. The question isn't whether we're alone. It's whether we're being watched, and what happens when we finally notice the eyes in the dark. Time is slippery when you're dealing with the cosmic scale, especially when messages might be crossing billions of light years at nearly the speed of light. Gamma-ray bursts don't just traverse space, they warp through it, contorted by the universe's own rules of relativity. Imagine shouting into a canyon where the echoes take centuries to return, only to realize the sound waves have stretched and twisted along the way. That's the challenge with GRBs. By the time their light reaches us, the original message, if there was one, might be unrecognizable, scrambled by the very fabric of space-time. Einstein taught us that time isn't absolute. Near a black hole or a neutron star, gravity bends time like a funhouse mirror. A civilization manipulating GRBs could be anchoring their signals near these extreme objects, exploiting relativistic effects to slow their local time relative to the rest of the universe. From their perspective, a message might fire off in a neat, orderly sequence, but by the time it reaches us millions of years later, those carefully timed pulses could smear into chaos like a record player slowing to a crawl, warping the music. Then there's the Doppler effect, but on a cosmic scale. If the source of a GRB is moving toward or away from us at near light speed, say, launched from a starship or a rapidly orbiting black hole, the burst's frequencies would stretch or compress like an accordion. A pattern of pulses meant to spell out prime numbers could arrive so distorted, we'd dismiss it as random noise. Even the burst's afterglow might carry hidden layers, its light redshifted or blue-shifted depending on the sender's motion. But the real mind bender is this: some GRBs might not be real-time signals at all. They could be cosmic postcards from civilizations long extinct. Imagine a society beaming a warning as their star collapses into a black hole. By the time the gamma rays reach us, they might be the last gasp of a culture that died out billions of years ago, their final words still echoing across an indifferent universe. We wouldn't just be decoding a message, we'd be reading a fossil. The universe doesn't just distort these signals, it censors them. Interstellar dust, magnetic fields, and the expansion of space itself all act like prisms, filtering out certain energies or stretching their arrival times. A burst that began as a sharp, artificial staccato might reach us as a drawn-out sigh, its structure eroded by eons of travel. And here's the haunting question: if we're seeing only the degraded remnants of a message, how many others have faded completely, lost in the static between the stars? Perhaps the most unsettling possibility is that we're not just reading fragments, we're seeing reflections. Some theories suggest high-energy gamma rays could ricochet off cosmic strings or warp around gravitational lenses, creating duplicates or time-delayed versions of the same burst. A single message might arrive multiple times, years apart, like an echo in a cathedral. If that's true, then the GRB catalogued in 1999 and its near-identical twin detected in 2023 might not be separate events at all. They could be the same scream bouncing off the walls of the universe. So how do we untangle this mess? One approach is to hunt for time-reversed signals bursts where the energy profile plays backward, a hallmark of certain relativistic effects. Another is to map GRBs against the cosmic web, tracing how their paths twist around galaxy clusters and dark matter filaments. If certain bursts consistently show distortions aligned with known gravitational lenses, that could hint at intelligent manipulation. But the deeper truth is this: every gamma-ray burst we detect is already a relic, a snapshot of violence frozen in time. Whether natural or engineered, these flashes are cosmic telegrams sent from the distant past, their senders likely gone, their contexts erased. Decoding them isn't just a scientific challenge, it's an act of archaeology, sifting through the ruins of events older than Earth itself. And if we ever find one that's more than just noise, it won't just rewrite our understanding of the universe. It'll force us to confront the fleeting nature of existence, that even the mightiest civilizations might only get one chance to scream into the void before silence swallows them forever. The moment we detect a gamma-ray burst with undeniable signs of intelligence, a sequence too precise, a pattern too perfect, humanity will face a crossroads unlike any in history. Do we respond? The question sounds simple, but the stakes are cosmic. On one hand, answering could unlock knowledge beyond our wildest dreams, secrets of physics, medicine, energy, even the nature of reality itself. Imagine receiving a library from a civilization millions of years ahead of us, compressed into bursts of radiation, but flip the coin and the risks are existential. What if our reply doesn't just start a conversation but invites annihilation? History offers grim warnings. When isolated cultures encountered technologically superior societies, the results were often catastrophic. Think of the Aztecs welcoming Cortés, only to be decimated by disease and warfare. In cosmic terms, a civilization capable of engineering gamma-ray bursts might view us with the same detachment we show ants. Would they share their wisdom or see us as pests to be eradicated before we become a nuisance? The dark forest hypothesis suggests the universe is full of hunters, not neighbors. By shouting back, we could be painting a target on Earth, yet silence carries its own dangers. If bursts are warnings, say, about an approaching galactic disaster, failing to respond might doom us. Consider the analogy of sailors ignoring a lighthouse's beam because they fear pirates. A civilization advanced enough to manipulate GRBs might be trying to shepherd younger species through cosmic upheavals we can't yet comprehend. Their message could be a lifeline, and ignoring it would be like refusing a vaccine because the needle looks scary. Then there's the middle path, listen but don't speak. SETI current protocols forbid transmitting replies to potential alien signals without global consensus. But gamma-ray bursts add a wrinkle. Their sheer power means any response would likely require energy on a scale visible across galaxies. Even a cautious hello could be like lighting a bonfire in that dark forest, announcing our presence to every civilization in the cosmic neighborhood. The ethical dilemma cuts deeper when you consider who gets to decide. Should a single nation or corporation speak for Earth? In 2016, a private group broadcast a message to a nearby star without international approval, sparking outcry. If we ever confirm a GRB's artificial origin, the debate won't just be scientific, it'll be political, philosophical, even spiritual. Some will argue replying is our destiny, the next step in evolution. Others will see it as reckless, a gamble with all of humanity's chips on the table. Perhaps the most unsettling possibility is that we've already missed our chance. If bursts are time-delayed by relativity, our response might reach a civilization long extinct, or arrive just as their patience runs out. Like casting a message in a bottle into a hurricane, we can't predict who'll find it or what they'll do when they do. The universe doesn't care about our fears or hopes, it simply is. And that's the heart of the dilemma. In a cosmos where the rules are written in gamma rays, is curiosity a virtue or a death sentence? Some of the most cutting-edge experiments in astrophysics aren't happening in telescopes or space probes. They're taking place in underground labs where scientists recreate slices of gamma-ray burst violence on Earth. Using facilities like the Extreme Light Laboratory or the National Ignition Facility, researchers can produce microscopic versions of these cosmic explosions by firing ultra-powerful lasers at tiny targets. The resulting plasma jets mimic the relativistic speeds and extreme energies of actual GRBs, allowing us to study their physics up close for the first time. These experiments revealed something startling. When scientists analyzed the light emitted by these miniature explosions, they found signatures eerily similar to those in certain anomalous gamma-ray bursts, specifically the way energy distributes across different wavelengths. Natural cosmic explosions tend to follow predictable thermal patterns, like embers cooling in a fire. But some lab-generated bursts, particularly those produced with carefully timed laser pulses, showed non-thermal spikes identical to oddities seen in space-borne GRBs. It's as if nature and human engineering can produce the same fingerprints under controlled conditions. Machine learning has become the game-changer in this hunt for cosmic breadcrumbs. Researchers feed algorithms with both natural and lab-simulated GRB data, training them to spot subtle deviations that human analysts might miss. One neural network at the University of California, Berkeley, recently flagged 47 bursts with suspiciously ordered light curves patterns where energy fluctuated in ways that mirrored experimental laser sequences. Even more intriguing, some bursts clustered in mathematical sequences resembling error-correcting codes used in human data transmission. The real breakthrough came when scientists combined these tools with quantum computing. By modeling how an advanced civilization might manipulate black holes or neutron stars, quantum simulations showed it's theoretically possible to tune a gamma-ray burst's properties by precisely controlling matter intake. The resulting energy profiles matched a subset of real-world GRBs with 96% accuracy, particularly those odd repeating bursts like GRB 110328A. What makes these experiments so valuable isn't just what they prove, but what they rule out. When a simulated artificial GRB and a cosmic one share anomalies that natural astrophysics can't explain, it forces us to ask uncomfortable questions. We're not just studying stellar physics anymore, we're potentially reverse engineering someone else's technology. Every laser pulse in these labs might be recreating on a tiny scale what some distant intelligence does with the raw power of collapsing stars. Gamma-ray bursts have ignited imaginations far beyond the realm of astrophysics, sparking countless stories where these cosmic flashes become bridges or warnings from civilizations beyond our own. Take Contact, the iconic 1997 film based on Carl Sagan's novel, where humanity's first alien signal arrives embedded in a burst of radiation. The movie brilliantly captures the awe and terror of decoding something so powerful it could only come from intelligence beyond Earth. What's fascinating is how closely the film's fictional scientists mirror real-world researchers, scrutinizing every pulse and frequency for patterns, just as SETI does today. Contact didn't just entertain, it introduced millions to the idea that the universe's most violent phenomena might carry deliberate meaning. Literature has explored this theme even deeper. Greg Bear's The Forge of God paints a chilling scenario where a seemingly natural gamma-ray burst is later revealed as an interstellar weapon, wiping out civilizations as casually as we might clear a chessboard. Then there's Blindsight by Peter Watts, a cerebral masterpiece where GRBs serve as cosmic stop signs, warning explorers away from regions of space where something ancient and unknowable lurks. These stories tap into a primal fear that the universe isn't just indifferent but actively hostile, and that the flashes we record might be the last thing a doomed species ever sees. Even blockbusters like The Avengers flirt with the concept. Remember the Tesseract, that glowing blue cube channeling enough energy to burn the world. Its power source behaves suspiciously like a contained gamma-ray burst, weaponized by advanced beings. While Hollywood exaggerates the science, the core idea resonates that harnessing such energy would require technology indistinguishable from magic. What's remarkable is how these fictional portrayals often precede scientific inquiry. Arthur C. Clarke's The Light of Other Days envisioned using cosmic phenomena for communication decades before researchers seriously considered GRBs as potential signals. This feedback loop between fiction and science is powerful. When Contact premiered, the idea of aliens using gamma rays was speculative. Today, projects like Breakthrough actively search for such signatures. Sci-fi doesn't just reflect curiosity, it fuels it, planting questions that later generations of scientists strive to answer. The darker side of this cultural fascination lies in disaster narratives. Films like Melancholia and Seeking a Friend for the End of the World depict GRBs as existential threats, capturing the visceral horror of an unstoppable force from the void. These stories reveal something profound about humanity. We're haunted by the possibility that the sky holds not just wonder but annihilation. Yet even here there's a twisted optimism. If we can imagine our demise, perhaps we can also imagine surviving it, or decoding the warning that saves us. Perhaps the most poignant example is his master's voice, Stanislaw Lem's brilliant novel about scientists struggling to interpret an alien signal that may not even be meant for us. The book's central dilemma, whether we're hearing a message or just imposing meaning on cosmic noise, mirrors the real challenges astronomers face with GRB anomalies. Lem's work reminds us that the greatest barrier to contact might not be distance or technology, but our own assumptions. This cultural tapestry does more than entertain. It shapes how we approach the unknown, training us to look for stories in the static. Every time a filmmaker or novelist imagines GRBs as something more than explosions, they're rehearsing humanity's next great revelation. That we might not be alone, and that the universe's loudest voices have been shouting all along. We just needed to learn how to listen. The next generation of telescopes isn't just improving our view of the cosmos, it's rewriting the rules of how we search for meaning in gamma-ray bursts. Take the James Webb Space Telescope, already revolutionizing infrared astronomy with its golden, segmented mirror. While Webb wasn't designed specifically for GRB hunting, its unprecedented sensitivity to afterglows changes everything. Imagine catching the faint infrared whisper of a burst from the universe's first billion years, a time when the first stars were collapsing into the very black holes that might have seeded advanced civilizations. Webb's ability to peer through cosmic dust means we're no longer blind to GRBs hidden behind interstellar clouds, potentially revealing bursts that previous telescopes missed entirely. Then there's the Cherenkov Telescope Array, or CTA, currently being built across 2 continents. Unlike traditional telescopes that capture visible light or X-rays, the CTA detects the shimmering blue glow of particles moving faster than light through Earth's atmosphere, a telltale signature of high-energy gamma rays. With over 100 telescopes working in concert, this system will catch GRBs with a precision we've never seen before, potentially identifying nanostructure in their light curves patterns so fine they'd be invisible to current instruments. If someone is encoding information in these bursts, the CTA could be the first to spot the microscopic irregularities that betray artificial origins. But hardware alone isn't enough. The real game changer is artificial intelligence, trained not just to find needles in cosmic haystacks, but to recognize needles that don't look like needles at all. At the University of California, Berkeley, machine learning algorithms have already discovered dozens of anomalies in existing GRB data that human analysts overlooked: subtle repetitions, energy spikes aligned with mathematical constants, even what appears to be nested patterns resembling error-correcting codes. These aren't your standard search programs. They're neural networks designed to think like alien communicators, testing millions of possible encoding schemes per second, from prime number sequences to quantum encryption protocols. The most exciting development combines these technologies. Picture Webb spotting a peculiar afterglow, the CTA mapping its high-energy structure in real time, and AI cross-referencing it against a database of simulated artificial bursts. We're not just building better tools, we're constructing an interstellar listening post, one that might finally distinguish between cosmic accidents and cosmic hellos. And the breakthrough could come from an unexpected direction. Last year, a team at Harvard demonstrated how quantum computing could analyze GRB data in ways classical computers can't, spotting correlations in the noise that might represent something far more startling: the universe's first recognizable sentence written in fire. While the idea of gamma-ray bursts carrying alien messages ignites the imagination, science demands we weigh every possibility, including those far less sensational. The cosmos is a laboratory of extremes, full of phenomena we've yet to fully understand. Before we attribute strange GRB patterns to intelligence, we must confront an unsettling truth. Nature itself might be the ultimate trickster, crafting illusions of design from sheer cosmic chaos. Take magnetars, for example, neutron stars with magnetic fields so intense they could erase a credit card from halfway across the solar system. These bizarre objects occasionally produce starquakes, violent ruptures in their crusts that unleash gamma-ray flares eerily similar to short GRBs. In 2004, magnetar SGR 1866 blasted Earth with radiation so powerful it temporarily ionized our upper atmosphere, Had it been farther away, we might have catalogued it as just another cosmic explosion. Yet its light curve showed peculiar fluctuations, tiny hiccups in energy that, if observed from another galaxy, could have been mistaken for artificial modulation. Then there's the puzzle of dark GRBs, bursts with weak or absent afterglows. Roughly 30% of detected GRBs fall into this category, their light seemingly swallowed by cosmic dust or unique physics we haven't deciphered. In 2018, researchers studying GRB 180705 found its afterglow dimmed 10 times faster than standard models predicted. The leading theory, the burst might have been jetting through a dense stellar nursery, its environment so thick with debris that the light was smothered on its way to us. Even the rhythmic bursts that seem so unnervingly orderly could have natural explanations. Binary black hole systems locked in deadly orbits might produce periodic gravitational waves that ripple through surrounding matter, triggering gamma-ray flares at precise intervals. Picture two whirlpools circling each other, each rotation squeezing out a burst of energy like clockwork. And let's not forget quantum foam, the seething fabric of space-time at microscopic scales where virtual particles blink in and out of existence. Some theorists suggest high-energy photons traversing this quantum turbulence could develop distortions mimicking artificial patterns. The real cautionary tale lies in history. In 1967, astronomers detected radio pulses so regular, they briefly considered labeling them LGM-1, little green men signals, the truth. They'd discovered pulsars, spinning neutron stars beaming radiation like cosmic lighthouses. Nature had fooled them with pure physics. Fast forward to 2017, when the repeating fast radio burst FRB 121102 had scientists speculating about alien megastructures until they traced it to a highly magnetized galaxy 3 billion light-years away. This isn't to dismiss the search for extraterrestrial intelligence, but to sharpen it. Extraordinary claims require extraordinary evidence, and the universe specializes in extraordinary natural phenomena. Every anomaly must be stress-tested against known physics before we leap to cosmic conspiracies. The irony, by ruling out every mundane explanation, we might stumble upon something truly unnatural. Like a sculptor chipping away marble to reveal the statue within, skepticism isn't the enemy of discovery, it's the path to certainty. So when the next strange GRB flickers across our telescopes, the real challenge won't be asking, is this them? But have we exhausted every other possibility? Because out there in the dark, nature's imagination dwarfs our own. Among the thousands of gamma-ray bursts recorded in astronomical history, one stands out like a carefully placed fingerprint on cosmic glass, GRB 090426, nicknamed the cosmic question mark by researchers who still struggle to explain its bizarre characteristics. Detected on April 26, 2009, this burst shattered expectations from the moment telescopes caught its light. While most GRBs fade smoothly, this one pulsed with eerie precision, 5 sharp spikes of energy spaced exactly 1.618 seconds apart, matching the golden ratio, a mathematical constant found throughout nature but never before seen in cosmic explosions. The anomalies didn't stop there. When scientists analyzed its afterglow, they found something even stranger. Most bursts emit light across a broad spectrum like a floodlight. 090426, however, showed narrow, almost laser-like emission lines at specific frequencies, including a prominent spike at 1.4 GHz, a frequency often associated with hydrogen, the universe's most abundant element. It was as if someone had taken a cosmic spotlight and filtered it through a prism, leaving behind a signature too orderly to dismiss as random. Even its polarization, the direction its light waves vibrated, defied natural models, twisting in a spiral pattern that one researcher compared to a screw threaded through space-time. Then there's the timing. The burst originated from a region of space devoid of galaxies, a cosmic no-man's land where no star large enough to produce a GRB should exist. Follow-up observations with the Hubble Space Telescope found nothing, no host galaxy, no remnant, just empty blackness. The most straightforward explanations collapsed under scrutiny. Colliding neutron stars, no nearby galaxies to house them. Dying massive stars, the environment lacked the raw materials to form one. The burst seemed to come from nowhere, a scream in the void with no visible screamer. What really set 090426 apart was its repetition. 6 weeks after the initial detection, the same patch of sky flared again, same frequency profile, same polarization twist, but this time with spikes spaced at 2.618 seconds apart, the square of the golden ratio. Natural cosmic events don't repeat with mathematical precision. Neutron star collisions are one-offs. Hypernova don't encore. Yet here was a signal that not only repeated but did so with a numerical consistency that echoed human-designed encryption protocols. Theorists scrambled for natural explanations. Could it be a previously unknown type of magnetar, spinning and quaking in some impossible configuration? Maybe a black hole consuming a dense object in bursts, like a bear gnawing at cosmic bones. Each hypothesis crumbled under scrutiny. Magnetars don't produce golden ratio intervals. Black hole meals don't serve courses with mathematical garnish. The only model that fit came from an unlikely source, a 2014 paper by physicist James Annis, who proposed that advanced civilizations might use GRBs as navigation beacons, encoding timing data in bursts to guide travelers through the interstellar dark. Critics argue pareidolia, the human tendency to see patterns where none exist. They point to the vastness of the universe, where even million-to-one coincidences must occasionally occur. But supporters counter that 090426 isn't just odd, it's precisely odd, ticking multiple boxes of artificiality simultaneously. Unnatural timing, engineered-looking frequencies, impossible location, and repetition with variation. It's the difference between finding a strangely shaped rock and one carved with unmistakable symbols. The most haunting possibility isn't that 090426 is artificial, it's that we might never know for sure. The signal's origin point lies 7.5 billion light-years away, halfway across the observable universe. Any civilization capable of engineering such a burst would be long gone by now, their message adrift like a bottle in an endless ocean. Yet its very existence forces us to confront a universe where the line between natural and artificial may be thinner than we ever imagined. After all, if something out there can sculpt gamma rays like clay, what else might be hiding in the cosmic noise? The universe has always whispered its secrets, but gamma-ray bursts don't whisper, they scream. Whether these cosmic explosions are nature's most violent accidents or something far more deliberate, their very existence forces us to confront a profound truth. We're living in a cosmos that doesn't just operate by rules, but might also contain rule makers. The possibility that GRBs could be messages or warnings from civilizations beyond our imagination isn't just science fiction. It's a scientific frontier, one where astrophysics meets archaeology, decoding the universe's loudest signals for echoes of intelligence. Every time a telescope captures one of these fleeting flashes, we're not just observing an explosion, we're standing at the edge of a cosmic crossroads. If even a single gamma-ray burst carries the fingerprints of design, it rewrites our place in the universe. We'd no longer be passive observers of the cosmos, but participants in a conversation spanning galaxies and epochs. The implications are staggering. Civilizations that mastered the energy of stars, bending the fabric of reality to send signals across the void. Their messages might be warnings of unseen dangers, invitations to a galactic community, or even the equivalent of keep out signs painted in gamma-ray light. Yet here's the beautiful paradox: even if every GRB turns out to be natural, the search itself transforms us. It pushes our technology further, refines our understanding of physics, and reminds us that curiosity is humanity's compass. Projects like Breakthrough Listen and Next-Gen telescopes aren't just tools, they're bridges to the unknown, built by generations refusing to accept that we're alone in the dark. So where does that leave us? However you interpret these cosmic enigmas, one thing is certain: the universe is stranger, wilder, and more mysterious than we've dared to imagine. Whether GRBs are natural wonders or engineered signals, they're proof that the cosmos still holds stories we've barely begun to read. That's why supporting space research matters, not just for answers but for better questions. Every time we point a telescope at the sky, we're not just collecting data, we're casting a line into the cosmic ocean, wondering what might tug back. The next time you look up at the night sky, remember, those flashes of light aren't just distant fires. They could be shipwrecks, lighthouses, or even flares shot by travelers we've yet to meet. The universe has never been silent. We're only just learning how to listen. So tell us, when you stare into the dark, do you see chaos, or do you see something waiting to be understood? The answer might change everything.